cosmic microwave background, or CMB, and it's like our universe's baby picture because it's a snapshot of what things used to be like very, very close to the beginning of time. And what we, the university scientists, were trying to do to answer that question that I showed you before was make the most high quality, most super detailed picture of the CMB that had ever been made before. But it turns out that it's actually really, really hard to do that from the ground with a telescope on Earth because the air in Earth's atmosphere blocks out the microwaves that are coming from space, from this glow all around us. So it's really, really helpful if we can take our telescope and lift it above most of the atmosphere. We decided that we were going to do this by taking our telescope and attaching it to a giant helium-filled balloon that would carry it nearly into space, so up to a height of 36 kilometers. That's 3 times higher than airplanes fly. And it's above most of that pesky atmosphere. But there was a problem. The problem is if we wanted to make that super high quality detailed picture of the CMB that I was telling you about, our telescope would need to be looking at the sky for a really, really long time, almost 20 days. And there's only one place in the whole world where you can launch a balloon and have it stay in the air for that long and not pass over any cities and not pass over any oceans. Can you guess where? Well, it turns out it's the frozen continent of Antarctica. So you see in Antarctica at the right time of year, the winds swirl around the South Pole like this. So you can launch your balloon from here and have it circle around the continent and in about 2 or 3 weeks and hopefully bring it back down somewhere close to where it started. All right, so once we built our telescope, we would have to then travel to Antarctica in order to launch it. Now, I'm just curious, maybe you can use the thumbs up or thumbs down feature or nod your heads, but how many of you listening to this think that this sounds like a little bit of a crazy idea? Yeah? Well, if you're thinking that this sounds like a little bit of a crazy idea, it's because it is a bit of a crazy idea. But at the time, we felt that this was the quickest way to get that high quality science data that we needed. And so we finally come to what I promised I would explain to you before, which is why is the telescope that I helped build, why did it have to be a robot? And the answer is because it was going up on that balloon. It was going up to a place where we could not follow it to fix it if anything went wrong. In fact, we couldn't even reliably send it messages to tell it what to do. So the telescope was going to be completely on its own up there. This telescope that we built, by the way, we called it Spider. And here's a picture of it that I took on the day that we launched it, way back in January 2015 from Antarctica. And a lot of you know what a smartphone is. I like to think of Spider as being sort of like a smart telescope because it had all these computers and sensors and gadgets built into it so that it would always know where it was, what direction it was looking in, and what it was supposed to be doing. But as you can see from the size of the people in this picture, Spider was a lot bigger than a smartphone. In fact, it weighs as much as an SUV. So because of that, we spent a lot of time trying to figure out how to make Spider work in the lab. One of the most challenging things was the motion systems. You can imagine that it can be hard to accurately point such a massive telescope when it's basically dangling from a string and keep it stable. But eventually we figured out how to get it to scan back and forth across the sky the way you're seeing in the video. And so we set off on an adventure. Back in 2014, 2015, I was part of the Spider project, which included this whole international team of scientists, as you can see. And we traveled to Antarctica via New Zealand. And once we got there, every morning at 6:30 a.m., we got on a special bus that could drive over the ice. And that vehicle took us out into the middle of what's called the ice shelf, which is kind of like a glacier. And once we were there, inside a set of special buildings, we got to work. We unpacked and assembled Spider, and we started doing the tests that we needed to do, the final tests to get it ready for the balloon launch. And you can see that sometimes when we were outside doing our tests, we would get special visitors coming by. It was Antarctica, after all. So eventually, after 3 months of work and a lot of setbacks, we felt that we were ready to attach Spider to the giant helium-filled balloon and launch it nearly into space. So I'm going to show you what that looks like now on this video. So you can see that the first thing they do is they release the balloon and it travels up over this vehicle here, which is the launch vehicle. And you can see that Spider's attached to the end of the giant crane that's sticking up from the top of the vehicle. So once the balloon is completely directly over Spider, it's going to be the driver of the launch vehicle's job to drive to the left and try and keep everything lined up. So he's basically chasing after the balloon, making sure that everything's lined up properly before they release the telescope into the air. So you can see that it's almost vertical. So he's going to start up the engine, and now he's driving. He's driving, but the winds are tough, and everything isn't quite lined up, and the balloon's moving pretty fast. Oh, don't worry, that was supposed to fall off, by the way. And so he's driving, and he's driving, and he's driving, and eventually he sort of can't keep up, so he just gives up, stops, backs up. Let's go. And with a twang, Spider is released into the brilliant Antarctic sky. We also put a GoPro camera on Spider, pointed back down at the Earth, just for fun. And this is the video from it. So this is the view that Spider had in the first few hours after launch. And the video is sped up by quite a bit, by the way. You can see that in the beginning, the telescope was spinning around and around uncontrollably. But eventually, once it got high enough in the air, we sent it a command to wake up the robot and tell it to stare in one direction. And you can see that it's just getting steadier and steadier. And from this point on, it was under its own control. So this actually worked during the flight. All right, so Spider's balloon carried it around Antarctica for a little bit over 2 weeks. And then it was time to bring Spider back down before it went out over the ocean. Unfortunately, Spider landed really, really far away from McMurdo Station, which is the base where we were living. More than 2,000 kilometers. But thankfully, with a little bit of help from the British, actually, who had a little supply base near there, we were able to recover Spider. Eventually, the weather cleared up enough for them to fly out there in a small plane to the crash site, pick up the most important pieces, and put them on a boat, headed out for South America. So the mission was a success. Now, being down in Antarctica for almost 3 months was the experience of a lifetime for me. And while I was down there, I saw some amazing things, including this emperor penguin who decided to stop by for a visit one day. And I would love to show you more things like that, but we got to stay on topic. And remember, the topic is robots in space. And so I'm only joking about the killer part, but hopefully, based on what I've explained to you, you can see that because of the really, really difficult science question that we were trying to answer, we needed to build a lot of advanced tech into Spider to make it completely automated, to make it robotic. Okay, so now we're going to switch gears a little bit. I want you all to take off your astronomy hats and put on your engineering hats, okay? Because we're going to be talking about building spaceships and space stations. Spider is what I worked on like 4 or 5 years ago. Nowadays, I'm lucky enough to be part of an exciting new project in space exploration, and it's called the Lunar Gateway. This is a new space station in orbit around the moon. So we haven't started building it yet, but when it's finished, it will be the most far away station that people have ever built. Just to give you an idea of how far away that is, right now, the ISS, or International Space Station, is in a fairly low orbit around the Earth. It's 400 kilometers up. Now, the moon, believe it or not, is 1,000 times farther away than that. And the plan would be to put the new space station in this kind of long and narrow orbit way out there in deep space. So the gateway would be built in stages, meaning that there would be several separate parts called modules that connect together to build up the whole thing, just like the ISS. But as you can see from this side-by-side comparison, unlike the ISS, the gateway would be quite a bit smaller and more focused in what it does. The Lunar Gateway would also be built through cooperation of lots of different countries. So at a very minimum, the United States, countries in Europe, Russia, and Canada would all be partners. So the Lunar Gateway is a global effort, kind of like how Mission X, which you're all participating in, involves people from all around the world. It's the same thing. So NASA would provide a module that has the solar panels and the rocket engines, and then the European Space Agency would provide a module for communications and science. And then there would be 1 or 2 modules with air in them where the astronauts could actually live and work. From time to time, spacecraft would visit the gateway and bring new crew members and new supplies, just like the Orion capsule, which you're looking at here, which is still being developed by NASA. But the idea is, with the Lunar Gateway as a sort of home base, astronauts could take Orion out for a spin and go on exploration missions farther and farther out into deep space, sort of like practice runs for a human mission to Mars. And I think that explains one of the main reasons why we want to build the Lunar Gateway in the first place. It's to use the space in between Earth and the moon as a place where we learn how humans can survive and stay healthy in deep space, because we don't really know how to do that right now. And we're going to need to know that if we're going to pull off a Mars mission. So to give you a sense, astronauts on the ISS are up there for about 6 months at a time. And while they're there, they can talk to Earth every day, and they have new supplies coming pretty regularly. But a Mars mission would be very different from that and much more challenging. The astronauts would be in space for up to 3 years, and they would only be able to talk to Earth a limited number of times, and that communication would have delays, and they wouldn't have any new supplies. They'd have to carry everything they need with them, water, food, fuel, for the mission with them. So the Gateway is a place to practice operating independently like that. So crew members who were on the Gateway would only be able to talk to Earth one day out of the week. The rest of the time, they're on their own. And new supplies would only come rarely because the Gateway is only planned to have astronauts on it 1 month out of the year. The rest of the time, the space station is empty and it has to operate by itself and maintain itself. So that is where Canadian technology comes in. The plan for Canada's contribution to the Gateway is new robots that would act as kind of like the Gateway's Swiss Army knife and repair worker all rolled into one. And these would be called the Deep Space Exploration Robots, or DSXR. And they would include a large robotic arm that has a lot of reach and can do the heavy lifting, and a smaller robotic arm that's less powerful, but can do finer, more detailed work, along with lots of special tools that would attach to the ends of the arms, letting them do lots of different kinds of tasks. So for example, the large arm could reach out and grab visiting spacecraft or Gateway modules, pull them in, and connect them to the rest of the station. While the small arm could go around repairing things like replacing batteries, solar panels, and cameras on the outside of the station. And that's actually really, really important because it means that astronauts would not have to go outside on spacewalks as often. And since spacewalks are expensive and can be dangerous, if the robot can do the work, it's better to let the robot do the work. All right, so here is an animation of DSXR in action. This is the large arm unloading cargo and installing it on the outside of the station. This is the arm putting a tool back into storage. And this is one of my favorite ones. Okay, this is the arm walking across the station. So it can walk end over end. The tip of the arm is going to attach and become the base of the arm. And the base of the arm lifts up and becomes the tip of the arm. And then the tip of the arm goes back down, attaches, and becomes the base. And the base of the arm becomes the tip. So in this way, the large arm can actually walk end over end. And here it is retrieving a tool and using it to swap out a broken part on the outside of the station. Okay, so at this point, I have another quiz question for you. Are you ready? Get your Slido apps out. Just going to bring it up. You just saw the large robotic arm in action. And here's my question for you. How many joints do you think the large robotic arm of DSXR will have? Is it 3, 4, 5, 6, or 7? Look at that. Answers are already rolling in. We're at up to 10, 14, 18. This is great. So looks like 3 is the leader, but 5 is a close runner-up. 7 is not a popular choice. Neither is 4. Wow, you all really like 3. Okay, all right. I think most of you have had a chance to answer at this point. So I'll leave the polls running, but I'll switch back to the slides. Okay, so those of you who said 3 are sort of right, because the large arm has an elbow in the middle of it, and then it has 2 wrists, one at either end. So that's 1, 2, 3. But that actually wasn't quite the correct answer to this question, because it was a tricky question. You see, each one of the wrists we consider to actually have 3 separate joints in it. And the reason for that is because each wrist has 3 different motors, these can-shaped things here, that allow it to rotate in one of 3 separate directions. And what we're going to do right now is we're going to do these motions ourselves. So I want everybody to stand up okay? So everybody stand up, and we're gonna start rotating. The first rotation I want you to do is side to side, like this, okay? Side to side. Is everybody doing it? Are you standing up? Side to side. This is just like what Spider was doing, right? So this motion is called yaw. Yaw? And all right, everybody stop that, okay? We're going to move on to the second of the three motions. Are you ready? This is just like Mission X astronaut training. It's going to give you a bit of a workout, but I want you to now bending at the waist, move down and up, down and up, down and up. All right? So that motion, that kind of motion is called pitch. That's down and up. Okay, all right, everybody stop that. Take a breather. Now we're gonna do the last motion, which is like this. Okay, I want you to lean left, lean right, lean left, lean right, lean left, lean right. Okay, are you doing it? So this type of motion is called roll, except we're not rolling all the way over because then you'd fall down, but we're just rolling a little bit. Okay, everybody can stop and sit back down. But basically, that is the reason why each wrist of the arm actually has 3 separate joints in it. It has to be able to do these 3 different movements. So the total number of motors in the arm is 7. There's 3 in one wrist, plus 3 in the other wrist, plus 1 in the elbow, makes 7. Okay, so while we're on the subject of Mission X, from what I understand, some of you have already had the chance to do this activity, whereas others haven't. But there is a challenge in Mission X for you to build your own robotic arm. And if you haven't done it yet, I'm going to give you some tips. One of the first things you want to consider, so first of all, the basic challenge is to build an arm that can grab something from far away. And one of the things you might want to consider is, do I want my arm to be long or short? And as a hint, remember that it was the large robotic arm of DSXR that was able to do the heavier lifting because it has more leverage. All right, another thing you might want to consider is how many joints is my arm going to have? Is it going to have an elbow in the middle, like a hinge? So that's another thing to think about. And then finally, and I think this might be the most important thing for this particular challenge, is what kind of tool or gripper or grasper am I going to build to put at the end of the arm that will give it a good grip on the object. And in the space robotic arms, the end of the arm that is able to grapple onto things is called the end effector. So what kind of end effector are you going to make for your robotic arm? Okay, so just to circle back to where we were at the beginning of this talk, recently we've had some really exciting news. The government of Canada announced that they were going to hire MDA to build the large arm and the small arm and the various tools of DSXR in the same way that MDA were the ones who built Canadarm2 and Dexter for the ISS. MDA are now confirmed to be the ones who are going to build the large arm and the small arm for DSXR on the Lunar Gateway. And can you guess what the official name of the large robotic arm on DSXR is? It's the Canadarm3. So this is awesome. This is amazing news because it means that everything I've shown you, which has just been concepts and computer models and drawings, is actually going to happen. Within the next probably 5 years or so, parts of the gateway are going to start going up. So I thought I would leave you today with a vision, one possible vision of the future of space exploration. Here are the advanced Canadian robots attached to the outside of the Lunar Gateway. And here is one of those visiting spacecraft I was telling you about approaching the space station. And what's going to happen is the large arm, maybe detecting it automatically, is going to move to reach it. is going to grab onto it, connect it, and pull it in closer to the space station. And now what it's going to do is actually keep it steady and present it to the small arm so that the small arm can take a piece of equipment off of it. So these are systems that people like you could be working on in the future. You could be working on designing and building upgrades to it, or operating it, or even working on future versions of these robots that are even operating even farther out into the solar system beyond the moon. So that's it for what I have to say today. Thank you so much for listening. I hope you really enjoy hearing about robots in space, and I can't wait to see your questions. Thank you again.
Thank you. Thank you so much, Jamil. That was absolutely fascinating to hear and to see space technology that is being developed at the moment, and your involvement in that. So we have about 10 or 15 minutes for questions, and we have quite a few that's come through on Slido. So I will give you a heads up when we've got one question or time for one question remaining. Otherwise, I'll hand over to you, Jamil, to go through the Q&A.
Okay, great. So everybody can still hear me, hopefully. All right, so I'm just looking through the questions here. We actually have a very large number of questions to deal with. Okay, so we have a question from Zidane, I'm not sure how to pronounce that, Virani, and asking, can robots act for themselves? And if so, how sophisticated can they be? And that's a great question. It's very similar to another question that was asked, which was, are robots totally controlled through NASA scientists or due to AI? Can they make decisions and react to certain issues on their own? And the answer to that question is robots that can make decisions for themselves using AI is the next step that we're trying to take. So on the Lunar Gateway, because the space station isn't going to have human crew members most of the time, we're going to need DSXR to be much more automated than Canadarm2 and Dexter are on the ISS. Right now on the ISS, Canadarm2 and Dexter are controlled by human operators using joysticks to drive the robots around. But on DSXR, we want to be able to build in some AI that can do some basic decision making. So examples of that are the robots being able to detect if they're getting too close to the station and avoid a collision, or the robots having cameras, and this technology is called machine vision, that can detect when a spacecraft is approaching or how close they are to those special bases that they grapple onto, so that they can automatically align themselves to those bases and grapple onto them and connect them without having to be, have the misalignment be corrected by people. The misalignment is going to be corrected in real time by the robot using feedback that it's getting from its own cameras. So that's some basic form of decision making that we're going to need those robots to be able to do. Okay, so another question is, how long do robots stay in space for? That's a great question. These robots are being designed to be in service for the full lifetime of the Gateway mission. So that's 15 years. And as you can imagine, for engineers like us, it's challenging to build something that is robust enough that it can actually continue operating for 15 years without breaking down. So that's part of the design challenge of building these robots, that they need to be able to be up there in space in, dramatically changing hot and cold temperatures and exposed to radiation for 15 years. All right. So okay. I promise I'm not ignoring this question. The most popular question on Slido is there life on Mars? And the answer to that question is we just don't know, but we haven't found any life on Mars yet or on any other solar system object. So we are not aware of any life existing on any planetary body other than Earth so far. So if there is life on Mars, we haven't found it yet, but also conditions on Mars are not super friendly for the kind of life that exists on Earth in terms of the temperatures being a lot colder and the atmosphere having a lot less oxygen. So that's the answer to that question. Do natural disasters happen in different planets too? Yeah, absolutely. You know what's a great example is one of the moons of Jupiter called Io. The name is literally just spelled I-O. And this moon is pretty close to the planet Jupiter that it orbits around. Because of that, Jupiter's gravity is actually stretching and squeezing the moon and causing a lot of activity. And so Io is full of volcanoes. There's a volcano erupting on Io like pretty much all the time. And so Io is volcano central in the solar system. So that's just one example of a planetary object in our solar system that is full of natural disasters, or what we would think of natural disasters if we were living there. All right. How fast do the robots move? That's a great question. The answer is that they move closer to the speeds that you saw in the final video of my talk, not the earlier video where the arm was walking end over end. That was sped up by a lot. So the robots, they move pretty slowly. And part of the reason for that is if they're carrying something really heavy, we need to keep the speed slow so that they can slow down to a stop from that speed without having too much force on the arm that might break it. So the large arm could be grabbing onto a spaceship or a gateway module that has a mass of like 10,000 kilograms. And when you're carrying something around that's that big, you want to move pretty slowly. So in that situation, the tip of the arm is only going to be moving at a few centimeters per second. That's it. So we got to keep the motions very slow, very controlled, and very precise so that we don't have a disaster on the space station. All right. How far into space can we send robots? Well, I guess it depends what kind of robot you're talking about. So out in the very distant reaches of the solar system, to the very far away planets like Jupiter and Saturn, we have sent spacecraft that are kind of robots because they control themselves. They're fully automated. And those are called orbiters. And so what they do is they either fly by the planet or they enter into orbit around the planet, and they have cameras and they can take pictures and send them back to Earth. So, we've sent robots like that all the way to the edge of the solar system and beyond at this point. In turn, we've also sent spacecraft that can enter the atmosphere of a planet out that far as well. So the Cassini mission, you may have heard of, had a separate little craft that detached from the main craft and was able to go down into the atmosphere of the moon Titan, I believe it was. And so, but in terms of landers, things that land on the surfaces of planets, and rovers, things that can drive around on the surfaces of planets, I don't think we've sent a rover any more distant than Mars. So that's about as far out as a robot that can land on the surface of a planet and drive around has ever gone. All right. Let me just see, I may have missed one of the more upvoted questions. What are you using the robots for? I think that was explained pretty well in the talk. It's so that we can build and maintain stations and spacecraft in deep space without humans having to be the ones doing the building, and as assistants to help us do the kind of science that we want to do. So another use for the robotic arm that I didn't mention was that if somebody has an experiment that they want to deploy, launch from the Lunar Gateway. The arm can help do that. It can pick up that science experiment and launch it into an orbit around the moon, or even on some other path. So that's another use that the robots could have, is assisting the launching of science experiments from the gateway. Do they get near to satellites? Well, there are no satellites all the way out there in lunar orbit, except for one, LRO, the Lunar Reconnaissance Orbiter. But in terms of the question, do the robots get close to the satellites that we have orbiting around the Earth to track weather and to provide internet and TV signals? We make sure that the robots that are attached to the International Space Station and the International Space Station itself is in an orbit that is different from the orbits of all those satellites, so that nothing collides into anything else, right? So I wouldn't say that the robots get near to satellites, except in the case that I just talked about before, where the satellite is one of the satellites that is being launched by that robot. All right. Did robots find life on any planet or any possibilities of life? No. As I mentioned before, we have not found life on any planet other than Earth yet. So we don't know if it exists anywhere else. Does sound travel faster in space? No, unfortunately, sound can't travel through space at all. So sound is waves of pressure in air or in some other material like water or even metal. So if you have a material and you can make waves travel through it, then you are producing sound. But in space, there is no material, it's a vacuum. So there's nothing for the sound waves to travel through. So in space, there's no sound. So that's the answer to Elena Casamoli's question. How are galaxies made? That is a very big topic in astrophysics. There are people who are spending their entire careers trying to answer that question. But basically, remember when I talked about earlier in my presentation how all the matter, the soup of the early universe was clumped up, and it got clumpier and clumpier with time because of gravity. So what we think is that most of that matter was dark matter, and it clumped together and it formed these halos, like concentrations of matter. And the regular matter, the atoms, started streaming into those halos and heating up. And that's eventually it heated up enough to form stars. So we think that galaxies are formed, or actually entire clusters of galaxies are formed in the places in the universe that had the biggest clumps, the biggest concentrations of these. All right, so unfortunately, we have time for only one more question, but I will be looking through these questions and answering some of them after the webinar as well. So the final question is going to be, what happens if the robots accidentally do something wrong? That's by Anaya Kabani, and that's a very good question. And the basic answer is, both on the ISS and on the Lunar Gateway, we have to build safety measures in. In fact, it's a requirement on MDA that the way our systems work, our robots work, is if any one thing goes wrong, we can still keep running and it's not catastrophic, right? So for example, let's say a motor breaks. It could either break and have the arm get stuck, or it could break in such a way that it keeps moving and we can't stop it. In that situation, we need a backup, right? We need a backup system that can prevent the catastrophe of the arm moving uncontrolled and smashing into the station, for example. And so maybe the backup in that case would be, if the motor is stuck on, we have the ability to cut power to everything, right? So you have to build space systems with a lot of backups in them, safety backups, so that if any one thing goes wrong, you're still okay. And actually on the International Space Station, it's set up in such a way that if any two things go wrong, you're still fine. So that's the answer to that question. And unfortunately, that's all the time we have today, but it was wonderful seeing all your faces, and these were excellent, excellent questions. I really look forward to going through the rest of them and trying to answer as many of them as I can. And thank you again for inviting me as a speaker today.
Thank you very much, Jamil. That was an amazing talk. I hope you guys all enjoyed learning about how robots are helping us to explore space. And a big thank you to Jamil for delivering the talk today.